Our next talk is Alex Hegedus from the University of Michigan. And Alex, go ahead and share your screen. He's going to be talking about simulations of the 21 centimeter imaging capabilities with the FARSIDE array. So Alex, it's all yours.
Thanks, Jack. Can you hear me and see my slides all right? All right. So thank you for having me. Again, my name is Alex. Listed here are some colleagues, also part of the FARSIDE team, continuing on in this very exciting vein of lunar radio science. All right. So again, just continuing on, this has been said before, but really the star of the show here is the redshifted 21 centimeter signal and its potential as an early universe probe. On the right are some different models of this signal and its absorption over redshift and frequency and age of the universe equivalently. And really looking below 40 megahertz is going to tell us a whole lot about the early universe. Lower frequencies show us older signals, and any deviation from the standard cosmology model allows us to quantify any newer exotic physics that we think are happening. So in particular, there's been a lot of talk about the global signal or averaging over a whole beam's worth of sky to get out this sky average feature. But what also would help quantify this exotic physics are looking at the spatial distribution or the spatial power spectra of this feature. And so here on the right is a movie from a data cube generated by a 21 centimeter fast run, where you just plug in a few different cosmological parameters and it simulates a possible 21 centimeter universe going all the way back for different redshifts. And so quantifying the spatial power spectra of this would allow us to more accurately pin down, aspects of dark matter, like we heard a couple talks ago. Here's an example of different simulations where they're injecting different levels of charged dark matter or changing the aspects of dark matter, and then showing the spatial power spectra of those different simulations. And so what you're seeing here is these blue and orange lines represent exotic physics scenarios where there is a relatively large fraction of charged dark matter, and this introduces more spatial structure in the sky. And only through imaging this can we actually tell this spatial distribution. Oh, I'm sorry, I have going back. Okay, right, and so we want to image this with as much fidelity as possible to back out and do these spatial investigations on the image of the 21 centimeter signal. And playing this image again, you can see that we're simulating 300 megaparsecs as a function of redshift or age of the universe. And so you can see that this 300 parsecs is getting smaller and smaller as a portion of the field of view in the sky. And so you see the axis slowly kind of zooming in. And that's because as we go further and further back in time to higher redshifts, 300 megaparsecs looks farther and farther away from our point of view. And so it's taking up a smaller portion of the sky. And so we're tracking that effect through an AstroPy Python code base, which can predict the angular size for a given redshift, for a given set of universal constants. Okay, and so now talking more about the other star of the show, FARSIDE, which wants to measure this signal and also map out this signal as a function of spatial. So we started out on the left. This pedal design is the old FARSIDE design, and it needed about 50 kilometers of tether, and it originally relied on a single rover to lay out all those antennae. That introduced a single point of failure, and we thought we could do a little better. So teaming up with JPL, us, the FARSIDE team, and some other engineers did a bit of development and landed on this multi-rover design where one rover per spiral arm. And we are going with the 4 spiral arm design because it gives us really good responses, and it also has great redundancy. So if one arm or one rover is dead on arrival, even without switching up the array configuration, we still have pretty good statistics on how good the recovering beam is. So even below 1%. And so, sorry, I'm jumping around here, but another cool thing about this updated FARSIDE design is that now we are adding in both polarizations, both vertical and horizontal. And so that's what's happening here is this zigzagging along for each rover that as it's laying down antenna, it gives both an X and a Y polarization right next to each other. And actually the fact that these are not co-located introduces some unique challenges in the polarization analysis, which Nivedita will talk more about later. But for now, I'm just going to be talking about total intensity. And so we've developed this a little bit more even to a Quasilog layout. So concentrating more antenna near the core of the array gives us better sensitivity.
You've got 2 minutes to go.
2 minutes, okay. So that gives us better sensitivity for having more shorter baselines. And so just looking at the point source function or the recovered dirty beam for a snapshot of this array, and you can see on the right here that the side lobes are below 1% as you move far away from the main central beam. And you can actually integrate this more. So what we're doing here is we're planting a simulated array on the lunar far side, imaging the spot of sky that is directly overhead at zenith, and then averaging over that for actually like 5 days, 5 Earth days. And that fills out our UV plane that you can see in the upper right corner, makes the point source function cleaner and improves our beam statistics. And so I'm going to move a little faster here, but we are able to add in synthetic noise to our simulated observations and make images for all the different frequencies that are in our data cube that we saw before. So on the left are truth inputs from 21 centimeter fast. On the right are dirty recovered images from our simulated FARSIDE array. And then this is again, more recovered images, but this time using the 5 days of integration time. So here's a side-by-side at 20 megahertz, just showing that you can improve the image fidelity and your signal to noise by doing this integration, and we can simulate that effect. And you can see that the color scales are a little off, but definitely the 15 time step recovered image matches this input truth by eye even, just a bit better than the snapshot, the single 8-hour snapshot. Let's see. Okay, so I think that I'll just wrap up here. So in conclusion, FARSIDE is looking really good. And the simulated output images are ready for spatial scale analysis to get out that K-vector analysis that will then help us better parameterize the different attributes of dark matter and other exotic physics. And so repeating this for different 21 centimeter fast runs with different underlying cosmological constants inserted, and then doing that analysis and showing FARSIDE can accurately estimate those parameters just through image analysis will be a really huge step towards showing that FARSIDE is worth doing. And in going the next step forward with these simulations, the next step is doing sort of what Neil suggested earlier, and that's modeling the whole field of view and the whole foreground of the galactic brightness from synchrotron emission, and then also modeling the other systematics of the beam and the antenna system, such as the long string of papers by Keith Tauscher and Jack's team at Colorado. So we're really sitting in a really great place, and go FARSIDE. I think that's it for me. Thanks.
Great, thanks, Alex. Appreciate that very much. We have a question from Nivedita Mahesh. For the Quasilog layout, what is the shortest distance between the antenna nodes? And was the mutual coupling effect taken into account?
Right. So this has gone through a couple different iterations, and in this layout, we've guaranteed placement of the antenna so that no antenna are closer than 70 meters from one another. And that is, you know, the minimum distance basically set by the neighboring orthogonal polarization pairs. And so these are the closest any two antenna ever get together. And that guarantees that, one, they don't overlap, and two, that mutual coupling is minimized, although I have not explicitly simulated that effect. So
I was going to say that's something, I mean, Nebedita raises a good point, because these wavelengths that we're looking at, these frequencies are very low. So that's part of what we need to do next. That's in the plan. So I think for time's sake, we need to move on. Thank you, Alex. A great talk.